Hey Stat Stars, welcome to AP Statistics. In this video, we'll be covering topic 2.10 over the binomial distribution. If you haven't already, be sure to download the guided notes that accompany this lesson from the Ultimate Review Packet for AP Statistics. There's a link in the description below. The guided notes will help you follow along and build a complete set of notes for the course. In this video, we will cover what the binomial distribution is and how once you know it, it will make calculating some tough probabilities pretty easy. As always, we'll begin by learning the key concepts and skills for this topic, and then we'll finish with AP-style practice problems to help you apply what we've learned. Let's get started, and always remember, one topic at a time, one step closer to a 5. So before we dive too deep into the binomial distribution, we first have to understand what a binomial random variable is. A binomial random variable is a very specific type of discrete random variable. So let's quickly remind ourselves what a discrete random variable is. So a random variable is the result of a random process is a numerical value. So it starts off with what we're going to be looking at today is random process, meaning we don't know what the outcome is, but the outcomes are listable numerical values. Discrete means listable and random variable means numerical values. So don't get overly confused. This binomial random variable is this crazy brand new thing. It's really not. It's something that we've been working with a lot. It's just a very special type that we're going to talk about exactly how it becomes special in this video. But at the end of the day, it's simply a random process where the outcome is a listable numerical value. Now here's the official definition of a binomial random variable. It's a little bit confusing, but let me read it anyway. A binomial random variable X, remember we typically use capital letters to represent a random variable, is a discrete random variable that counts the number of successes in repeated independent trials that have only two possible outcomes, success or failure, with the probability of success P and the probability of failure being 1 minus P. So the idea is that a binomial random variable, the outcomes are the number of successes that you could have in a set number of n trials, n just being a placeholder for how many. So for example, let's just say that Doug has a 15% chance of hitting a bullseye with a dart. And we know automatically that if he has a 15% chance of success, that's hitting the bullseye, then the complement would be the 85%, which would be 1 minus P, and that is where we get failure. And if he shoots, let's say, 5 darts, he's going to shoot 5 darts. The random variable, the binomial random variable, is how many successes he has, how many times he will successfully hit the bullseye. So if he has a set number of darts, 5 darts, he could hit all 5 of them. That'd be awesome, right? He could hit 4 of them, he could hit 3 of them, he could hit 2 of them, he could hit 1 of them, or oh my gosh, he could hit 0 of them. He can't hit a negative amount, that doesn't make sense. He can't hit more than 5 because he's only shooting 5 darts. And he can't hit a decimal amount because how do you have 3.6 bullseyes? That doesn't make sense. So again, this is discrete random variable. The outcomes are listable numerical values, and those outcomes represent the number of successes that he could have in n trials. And every trial, the probability of success is 15%, and then failure would be the opposite of that, 85%. Now, the other key thing here is we have to have what are called independent trials, which means that what happens on one trial doesn't change the next. It's not like there's any conditional probabilities going on here where we say, well, if he hits the first 2 bullseyes, then the probability of hitting him the 3rd bullseye will go up to 90%. No, none of that happens. The probability of success stays the same. So that is a binomial random variable described pretty quickly. Now, let's break it down a little bit deeper. There is a way that we could make sure that we have a binomial random variable, and there's 4 things that we have to check, and all 4 of these things are in that definition, but we're just going to break it down individually. The first is that every trial has to be what we call binary, meaning that it could either be a successful trial or a fail. Only 2 things can happen on every trial. What we want to happen or it doesn't happen. So that's it. It's got to be binary. That's why it's called a binomial random variable. The second thing is that those trials have to be independent. There could be no conditional probabilities here. Well, if this happens, then that happens. But if this happens, then this goes down. No, none of that. It has to be independent trials, which means what happens on one trial, success or fail, has no bearing on the next changing or being higher or lower. And then the third thing is we have to be given a set number of trials, right? Because we need to figure out how many successes we could have in n trials. So n, the number of trials, must be given to us because otherwise it would just go on forever and ever. And the fourth and final thing is that the probability of success, whatever it is given to you in the problem, we call that P, well, it has to stay the same. It cannot change from trial to trial to trial. And that means the probability of failure, which is the opposite or the complement of the probability of success, must also stay the same. Now, one way we could remember this is using an acronym. We can remember B for binary, I for independent, T for number of trials, and S for probability stays the same. So if we remember the acronym BITS, B-I-T-S, we can remember the four things that we have to check to make sure we have a binomial random variable. All right, let's look at a couple of examples. This first one says Mackenzie makes 78% of her free throws. If she shoots 8 free throws, let the random variable M be how many she makes. So the question we have to answer, is the random variable M a binomial random variable? Well, let's check our bits. First, is it binary? Every shot, she's either going to make the free throw or she's going to miss it. It's either going to be success, it goes in, or failure, it does not. That's definitely binary. Independent means that there's no conditional probabilities. It's 78% every single time. It's not like if she makes the first, the probability goes up, and if she misses the first, the probability goes down. So we have independent trials. And then T is a set number of trials must be given. In this case, we were told we have 8 trials. So we're going to either make all 8 free throws, 7, 6, 5, 4, 3, 2, 1, or no free throws. Those are the only outcomes for this discrete random variable. And then lastly, we have S, the probability must stay the same. So we can't have any assumption like there's no hot streaks. Like, oh, Mackenzie made 4 in a row. Now the probability is going to change to 80% or 85%. Nope, the probability of success must stay the same. So this would be considered a binomial random variable. How about the second one? Kayla makes 80% of her free throws. But if she makes any one free throw, the probability of the next one is a make increases by 2%. So if she makes the first, then the next one's 82%. And if she makes that one, then it goes 84%. But if she misses a free throw, it drops down 10%. She shoots 10 free throws. Let the random variable K be how many she makes. All right, is this binomial? Well, first let's check our bits. B binomial, yes, it either goes in or it goes out. Independent. Do we have independent trials? And that is where we fail because we have some conditional probabilities. If she makes a free throw, it goes up 2%. If she misses a free throw, it goes down 10%. That violates independence. That means what happens on any one trial impacts the next. And that violates the rules for binomial random variable. This is still a random variable, but it's not going to be a binomial random variable. So sorry, this doesn't meet the requirements. Also failing is the S that stays the same. The probability certainly does not stay the same. We're literally telling you that it's going to change. All right, let's look at a third example. In a small bag of 20 candies, 25% are red. Okay, 20 candies, 25% are red means that there are 5 red candies. 5 out of 20 is 25%. If 5 candies were selected without replacement, let R be the random variable for how many candies are red. Okay, let's check our bits. Is it binary? Yes, the candy's either red or it's not red, so that checks out. Is it independent? Does the probability stay the same? And does each trial not have to do with the next? Well, this is where we run into a problem again. It says we're selecting without replacement. So that means the first time I reach into the bag, there are 5 out of 20 red, which is 25%. Now, the next time I reach in, the probability is changing, right? Because if I got a red one, well, now there's only 4 red left out of 19 that are left in total because I did not replace it. So 4 divided by 19 is 0.211%. So the probability clearly changed. Now it's 21.1%. And then even if I did not get a red, well, that means there's still 5 red ones left out of 19. So again, the probability is still changing even if I did not get a red one. So 5 out of 19 is still 26.3%. So now the probability went up to 26.3%. So we also violate the probabilities are not staying the same, and that means they're not independent. So what happens on this very first selection could impact the next or the next, and so on and so on. So again, this is not a binomial random variable. Now this next example is going to be very similar with a little bit of twist that will make it binomial. So just hear me out on this one. At the candy factory, there's a batch of millions of candies. 25% are red. Okay, so 25% of millions, well, I don't even know what that'd be because it doesn't tell me the exact number, but it would be a lot, right? Okay, so if 5 candies are selected without replacement, let R be the random variable for how many candies are red. Okay, is it binary? Yes, it's either going to be red or it's not going to be red. Now, do we have independence? Well, this is where it's a little bit tricky. Yes and no. Oh, hear me out. I know that's weird. All right, let's just say there was exactly 1 million candies. Now, I know it said millions, but let's just say there's 1 million. Okay, so if there's 1 million candies, try to make sure I get all my zeros here. Okay, I think that's 1 million. That means 250,000 of them are red. And that would be the 25%, right? Now, let's just say that we do get a red marble. Like we pick out a red marble. It says without replacement, so we don't put it back. Well, now there's 999,999, okay, whatever. You get the idea. There's 999,000 marbles left. And then how many of them are red? Well, 249,999. So has the proportion of red marbles technically changed? Yes. But if you do the math on that, 249,999 divided by 999,999, it is 0.249999999. So technically, has it dropped, right? It's no longer 25%. It's a little bit different. But it's so close that we say that it's negligible, meaning it's not that big of a difference. So again, has independence been violated? Yes, because I got a red marble on the first selection and the probability of the next one being red changed a little bit, but it didn't change enough. See, up here, it changed significant. It went from 25% to 21.1%. That is a noticeable change that violates independence. But here, it's not a big enough change. We actually have something called the 10% condition we'll talk a little bit more about later on. But the idea is if the number you take out is less than 10% of the population, you are still violating independence, but it's not a big enough deal that it's going to really matter, and we can still proceed with a binomial random variable. Now, again, did we check our bits? So we're going to go do the T for trials. We were told that we have 5 candies. That's our N. And then the probability of success, again, technically it's not staying the same, but it's a negligible difference because, again, it's so many M&Ms. It's not even millions. So even if we made that 2 million or 3 million, it's even going to be a smaller change. So even though we're taking red ones out, the probability is pretty much staying the same, which is okay. It's not exact, but it's okay. And again, that's something called the 10% condition that we're going to talk a lot more about later. All right. So now let's talk about actually some examples here, because now that we understand what a binomial random variable looks like and we understand the outcomes of that binomial random variable or how many successes that you could have in N trials, now what we want to do is talk about calculating probabilities for a binomial random variable. And this is going to get a little bit confusing before it gets really, really easy. So just bear with me here. All right, let's go back to Mackenzie. Mackenzie makes 78% of her free throws. If she shoots 8 free throws, let the random variable M be how many she makes. We want to construct a probability distribution. Now remember, a probability distribution is going to be a list of all of the outcomes, and since binomial is discrete, we can make that list, but we also have to have all of the probabilities of those outcomes, and that's what we got to start teaching you right now. So first off, here is the list of all of those outcomes. If she shoots 8 free throws, how many can she make? 0, 1, 2, 3, 4, 5, 6, 7, 8, or that's it. Can't make 9, can't make 10, she's only shooting 8, and can't make decimals, can't make negatives. You get the idea. All right, now what we want to do is start breaking down how to calculate each of the probabilities. And this is where we're going to have to use some of our probability rules, especially what's called the general multiplication rule, because she's shooting multiple free throws, we're going to need to multiply. So let's start with the very first outcome of 0. All right, what's the probability she makes 0 free throws? Well, there are her 8 shots, and we need all of them to be failures. Every single one of them is a failure. Fail, 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 fail. You get the idea. Now, what's the probability of failure? Well, if there's a 78% chance she makes it, there's a 22% chance she misses it. So we have a 22% chance that she misses the first, 22% chance she misses the second, and so on. All those probabilities stay the same. They don't change. They don't go up. They don't go down. That's why it's 22% the entire time. We do have independence, which means if she misses 5 in a row, it's still 22%. Now, how do we calculate the probability of this? Well, it's the general multiplication rule, because we need this to happen, and then this, 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 and then this. So we're just simply going to multiply 0.22 times itself 8 times, but we could use exponents to make that a lot easier. So if we do 0.22 raised to the 8th, that's repeated multiplication, we get our probability of 0.0000549, which means it's extremely unlikely that she misses all the free throws, and that makes sense because she's actually a pretty good free throw shooter. She makes 78% of them, so she shouldn't miss all of them, but it's not impossible, but it's very, very unlikely. Now, I do want to present this to you in a slightly different way. It's very similar, but slightly different because it's going to help us later on when we start to look at a formula for doing this. All right, here's another way that we could think about this probability. Now, we have to think about all of her 8 shots, and we have to think about both successes and fails. Now, what we just talked about is the fact that she has 8 failures. She literally misses every single shot. That means that there are no successes. So I really don't need this 0.78 to the 0. And you guys should know that anything raised to 0 is 1. And when you multiply by 1, it does nothing. So I don't really need that, but I want to make sure we're accounting for how many successes there are and how many failures there are. She's missing all of them. So she has 8 failures, which means she has 0 successes. And this one represents the fact there's only one way this can happen. And here's it. We're looking at it right now. All 8 are failure. You can't switch any of those around and have it look different. All 8 failures is all 8 failures. There's only one way that can happen. Now, you might be like, why did you do that? Well, you'll see here in this next example. All right, let's talk about the probability she makes one of them. For example, maybe she misses. There's our success. The 4th shot is our success, and then another 4 misses. That end result is her making 1. Now, what's the probability of that? Well, we have to break down each shot. So we have 22%, 22%, 22%, and then the success, 78%, and then another fail, 22, 22, 22. 22. Again, we can use exponents to make this a little bit faster. So this is where we have 0.78 raised to the 1st for her 1 success, 0.22 raised to the 7th for her 1, 2, 3, 4, 5, 6, 7 failures. So again, that's me multiplying this out for this one scenario. But the problem is this. Yes, this is the probability of this one very, very specific outcome where she makes the 4th. The one shot she makes is the 4th shot. But what about it being the 2nd shot? Technically, this is a different scenario where she makes her 1 make is the 2nd shot. Now, the good news is that the probability still stays the same because when you're multiplying, order does not matter. So at the end of the day, we still have 1 success, 0.78 to the 1st, and 7 failures. But this scenario right here, where the 2nd shot is her make, is different than this scenario where it was the 4th shot. So the idea is, how many different scenarios are there? Well, there ends up being 8 of them because she can make the 1st, miss all the others, make the 2nd, miss all the others, make the 3rd, miss all the others, and all the way down the line. So there's 8 different scenarios. But here's the good news. They all have the same probability because they all have 1 make, 7 misses. And when you multiply that out, no matter the order, you get 0.0000195. So now we're going to put all of this together to get the total probability she makes 1 shot. Here it is. So she makes 1 shot. So we need 1 78%. We need 7 22%. But there's 8 different ways that this can happen. So there's 3 parts to this formula for the probability. How many successes there are, that's our P, probability of success. How many failures there are, that's the 1 minus P, the failure. And then how many different combinations there are, right? I'm going to put combos there. How many different combos there? Like, meaning if she makes 1 shot, how many different ways can that happen? Well, again, which one is the make? This one, or 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 this one. There's 8 different ways. Now, back when we did 0 makes, all 7 misses, well, there's only one way that could happen, which is why I wrote it that way for you. All right, so hopefully this is starting to be processed a little bit, but now let's move on and keep going and looking at 2 shots. She makes 2 shots. What's the probability she makes 2 shots? Okay, so here is one combination, one option for this. She makes the 2nd and she makes the 6th. Okay. All the others are failures. Now, what would this look like probability-wise? Well, let's use exponents to speed it up a little bit. We have 0.78 to the second for her 2 makes, and 0.2 to the 6 for her 1, 2, 3, 4, 5, 6 failures. Again, we have to have all 8 shots accounted for, and if 2 of them are makes, 6 of them are failures. Now, remember, multiplication, I don't have to multiply in order. So yes, officially it's 0.22 times 0.78 times 0.22 times 0.22 times 0.22 times 0.78 times 0.22 times 0.22, but it's okay if I do it out of order because multiplication says that. But now we got to think about the fact that there are other options. Like this one was making the second, making the 6. What about this one where she makes the 3rd and she makes the 8? This is a different scenario, but it ends in that same outcome of 2 made shots. Now again, probability, good news, order doesn't matter, so the probability is the same as the previous example, but it is different. We still have 2 makes and we still have 6 misses. All right, so now what we got to do is figure out how many different outcomes are there for making 2 shots. See, that's where it gets tricky. Like maybe this is the make right here, and this is the make. Now again, the probability would still be 0.78 squared times 0.2 to the 6, but it is a different outcome. Well, there ends up being 28 of them. There are 28 different outcomes. I'm not going to walk you all through all of them because you're going to get very bored. But the good news is all 28 of those outcomes have the same probability of 2 makes, 6 misses, and there's that final probability. So now we're going to get back to our final answer. Again, this is going to be coming from a formula. So that's why I'm kind of going in a nice organized way here. So we have 2 makes, that's our probability of success. 6 misses, that's our probability of failure. And then we have the 28 is how many different combos there are. There are 28 different combinations. Now, one thing you might be wondering to yourself right now is how the heck did you know there were 28 different combinations? Well, one thing you could do is literally walk through them all. Okay, could be the 1st and the 2nd, could be the 1st and the 3rd, could be the 1st and the 4th, could be the 4th and the 8th. And then you drive yourself crazy trying to think of them all. But we have a shortcut. Now, hear me out. I'm about to show you this shortcut to figure out the number of combos. You're not going to like it. The math is a little bit weird, and you might not even recognize some of this math, but don't worry, because I'm going to show you how your calculator could do all of it for you, so don't stress over this. But this goes back to something that you might have learned, I don't even know, back in another class, over combinations. A combination is the number of ways to choose X items from a set of N items where the order of selection does not matter. Now, there's actually 2 different ways that we mathematically notate this. We could use this right here, where we're saying, okay, in our case, we have 8 shots. We want to choose 2 of them to be makes. How many different combinations are there? Or another way we can notate it is with these giant parentheses, where we do 8 shots on top. How many different ways can we choose 2 of them to be makes? And then we use this crazy formula with these factorials. If you don't know what a factorial is, like for example, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, again, don't stress because you're not going to have to use this formula, I promise, but it's going to end up looking like this for our example. We have 8 shots, and we want to see how many different ways 2 of them could be successful. If you put it all into this formula, you do get 28. But listen to me, do not stress. You will never ever need this formula. Desmos comes to the rescue because you are allowed to use Desmos on the exam. So if you go to Desmos and you pull up the keyboard and you go to functions, at the literally the very bottom is NCR. So in parentheses, you're going to type in the number of trials you have, in this case 8, comma 2, that's how many successes we want. And look, right there, it gives you 28. So that's how we can figure out that there are 28 successes in 28 combinations where you have 2 successes in 8 trials. Now, I'm going to make this even easier for you in a couple minutes, so do not stress. All right, so that is how we can figure this out. Now, let's actually use this formula to speed up this process. How many different ways can she make 3 shots? What's the probability she makes 3 shots? Okay, here's one option where she makes 3 shots. And again, the probability would be 0.78 to the 3rd, 3 makes, and then 0.22 to the 5th for her 5 misses. Because if she makes 3, she must miss 5. But what we want to figure out is how many different combinations there are. We want to figure out what is 8 choose 3. How many different ways, if you have 8 shots, could 3 of them be successful? Well, again, all you got to do is use Desmos. Don't stress over using a formula. So again, we're just going to go all the way down on that functions tab. And we're going to do 8, 3, hit enter, and there it is, 56 different combinations. So now we're going to come back here and we're going to get our answer. So we have 0.78 to the third. That's for the 3 makes. That's what we needed. 0.22 to the fifth. Again, 8 minus 3 is 5. If you have 8 shots and 3 of them are makes, then the other 5 have to be misses. And then this simply tells you how many combos there are, which we just figured out on Desmos is 56. So there's 56 different scenarios that result in 3 makes. All of those scenarios have the same probability of 0.78 to the third times 0.2 to the fifth. Multiply all that out and we get the probability. All right, what about the probability of 4 makes? Now I'm going to go through this a lot faster because we know the process. So first we have how many different combos there are. 8 choose 4. That's going to tell you how many different combinations there are. We have 4 makes, which means we have 4 misses. And then we calculate all that out. We could use our calculator to do the 8 choose 4 part, and then we get 0.0607. Now just keep watching this video, please. Don't stop now because I'm going to make it even easier here. All right, what about 5 makes? Well, same thing. 8 choose 5. 5 makes, which means there's 3 misses. Multiply all that out, we get 0.172. Just make sure that you truly understand the 3 parts. This is the number of combos there are that result in 5 makes. This is the number of successes, P, and this is the number of failures, 1 minus P. All right, now let's do 6. Well, 8 choose 6, that's the number of combos. 0.78 raised to the 6 times 0.22 raised to the second, makes 6, miss 2, 0.305. That's actually pretty likely. Remember, she's a good free throw shooter, so she should make 6 free throws. And what about the probability she makes 7? Well, again, 8 choose 7, 0.78 raised to the 7th times 0.22 raised to 1, 7 makes, 1 miss. 8 choose 7 is how many combos there are, and we get 0.309. And one more thing I want to comment. If you don't want to use this notation, you could use the big C notation like that. Now, statistically in AP Stats, this is the notation we prefer. But again, you're not even using the formula. You're just using your calculator anyway. All right, and the last one, 8 makes. She makes every single one of them. Well, again, this would be 8 choose 8. 8 shots, all 8 of them are successful. Now, that is only one way that can happen. Success, 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 success. You get the idea. And then all 8 are makes, 0.78 raised to the 8th, and then we have 0.22 raised to 0 because if she made 8 of them, then she missed none of them. And our final probability there is 0.137. So here is the final probability distribution with literally all of the outcomes listed and all of the connected probabilities that we just showed you how to calculate. Now that we understand the process, let's look at a generic formula. Here is the formula for binomial probability. This first part is the number of combinations there are. Again, I call them combos. How many different combos are there? Now remember, you don't have to know that crazy formula, the calculator will do it for you, but N is the set number of trials you have, X is the number of successes you're looking for. Then you have your successes. P is the probability of success. It's going to be raised to X, the number of successes you want to happen. Then you have your failures. 1 minus P is the probability of failure, and that's going to be raised to the N minus X. Now, where do we get N minus X from? Well, for example, if we have 8 trials and we want to make 3, well, 8 minus 3 means there would be 5 failures. So if you do N minus X, that should tell you how many failures you have. Most kids are just going to figure that out in their head. But that is the formula for the binomial function. This is going to calculate the probability of each individual outcome in a binomial formula. Now, here's the best part. This formula is awesome. I love it. You need to know it and understand it, and hopefully this video is doing that for you. But there's also cheats that could do all of that math for you, which is going to come in super handy on multiple choice questions or even free response questions where you just have to get the answer. There are cheats on the numerics calculator, or there's cheats on the TID4 calculator, and there's also cheats on Desmos that could do all the work for you. And I want to walk you through another example where we do all of that for you on Desmos, and you're going to love it. It's going to be so easy. All right, but there's one more thing I'm going to teach you before we dive into some examples. Let's now talk about the parameters of a binomial random variable. Now remember, the parameters are the mean and the standard deviation if the random variable were to be repeated a large number of times. So if we were to repeat this scenario, the average or the mean or the expected value is what we would expect in the long run. And this is a really, really easy formula, N times P. Think about Mackenzie for a second. If she were to shoot 8 free throws over and over again, shoot 8, shoot 8, shoot 8, shoot 8, and maybe she did it multiple times, day after day after day after day, and she kept a journal, and every day she wrote how many she made of those 8. N times P is just going to be the average in the long run. It's going to be the average of all of those trials. So if we have 8 shots and the probability of success is 0.78, 8 times 0.78 means that on average, we would expect her to make 6.24 free throws. Now, in any one trial of shooting 8 free throws, she's never going to make 6.24. It's impossible. She can make 6, she can make 7. But listen, it's the average. It's what we expect to happen in the long run. So if, before Mackenzie steps up and shoots her 8 free throws, I would expect her to shoot 6.24 makes in the long run, okay? Pretty simple. Then we have the standard deviation. Well, because guess what? This 6.24 is going to vary. Some days she might make more out of 8. Some days she might make less. So the formula here is N times P times 1 minus P. So what we're going to do in our square root here is we're going to do 8 times 0.78 times 0.22, the probability of failure. So don't forget that square root. 8 times 0.78 times 0.22 is 1.17. So yes, we expect her to make 6.24 free throws, but sometimes she could make a little bit more, she could make a little bit less. So make sure you understand these, but be very careful. These formulas right here only work if you are a binomial random variable. They don't work for any other discrete random variable, only binomial random variables. All right, now let's dive into a full example, and I'm going to show you how your calculator is going to do so much of it for you. All right, worldwide, 13% of people are left-handed. In a random group of 20 people, let H be the number of left-handed people. Now, the first thing we want to do is make sure it's binomial. So let's check all of our rules. First, it's binary. A random person is either going to be left-handed or they're not. It's independence. If I'm left-handed, that's not going to make the next person any more or less likely to be left-handed. And we're talking about a population of millions of people in the world. So if I take out 20 of them, yes, maybe I'm technically violating independence, but it's not that big of a deal. It's kind of like our candy problem. There's millions of candies and you take out 5. Yes, the probability might not still be 25%, but it's going to be really, really close where it doesn't matter. Now, we were also told a number of trials, 20 people, N equals 20, and the probability of success must stay the same. It's not like 13% is contagious, where if one person's left-handed, they're going to spread it to the next and the next and the next. You get the idea. All right, now let's answer some questions. What is the probability that exactly 6 people are left-handed? Well, yes, let's use our formula, right? We just taught you how to use the formula here. So what's the probability of 6 left-handed people? Well, first is the number of combinations. How many different combos are there? All right, well, what 6 people are left-handed? Well, there's lots of different scenarios. Well, 20 choose 6 is going to tell that for us. Then we have our success, which we need to raise it to the 6 because we need 6 left-handed people. That means the other 14 people are all failures, and that's 1 minus P, and 1 minus 13, or 1 minus 0.13 is 0.87. So we get 0.0266. Now, what I want to show you is you don't have to calculate this out. You don't have to go to your calculator to figure out the combos. You don't have to do any multiplication here. You do need to understand this formula and why it is what it is, but watch this. This is the amazement of Desmos. All right, if we go to Desmos here, I'm going to clear this out. All right, if we click on this little plus button right here, and we go to inference. At the very top is probability distributions. Now, there's a drop-down menu here, and we need to find binomial. There it is right there. Now, it's going to ask you for 2 things. The probability, not the probability, it's going to ask you for the number of trials, ED, in this case, 20 people. And it's going to ask us for the probability of success, 0.13. Those are the only 2 things it needs. Another reason why it's called the binomial model, because there's only 2 things you need. All right, hit create distribution. Now, first off, look at this picture. Look how cool this is. This is literally the probability distribution. All you got to do is click on each dot. So this first dot would be 0 people are left-handed, and right next to it is the probability. This next dot is 1 person and the probability. Then 2 people, 3 people, 4 people, 5 people, and here's what we were asked for. The probability that there are 6 left-handed people is 0.0266. All we had to do was find that dot. So it's literally building you a distribution. So look at what we see here. We see that there's a higher probability of, 1, 2, 3, 4 left-handed people. That's all kind of likely. But the more people that are left-handed gets more and more unlikely. For example, the probability that there are 18 left-handed people is extremely low. Now, they just put a 0 here. It's technically not 0, but it's like 0.0000000000000, then it might as well be 0. It's very, very unlikely. All right, so we go back to it. That's how easy it is to get the 0.0266. So yes, you have to understand this formula, but you don't have to use it. You could use your calculator. All right, let's do another one here where it might get a little bit tricky. What is the probability of at least one left-handed person? Okay, so at least one means one or more. So with 20 people, we could have anywhere from 0 lefties, 1, 2, 3, 4, 18 lefties, 19 lefties, or 20 lefties, right? There are a lot of outcomes, but they are still listable. Now, at least one means that we want to add or we want to combine all of these, right? We want to do at least one or more. We got to find that probability. So one thing we could do that we're not going to do, but one thing we could do is calculate the probability of 0. Oh, excuse me, sorry. Calculate the probability of 1, then calculate the probability of 2, then calculate the probability of 3, then calculate the probability of 4, and then basically add them all together. So if I actually go back to this model here, I could find the probabilities of everything except for 0, not 0. Find the probability of 1, 2, 3, 4, 5, 6, all the way up to 20, which again is pretty low, basically 0, and then add them all together and I'll get my answer. But there's an easier way. The only outcome I don't want to happen is 0. So if I find the probability of 0 and then do 1 minus that probability, I'll get with everything else. Again, I want 1 all the way up to 20. So if I just do 0 and then do 1 minus 0, I will find the probability very, very quickly. So again, here's me showing my work for 0. Here's the number of combinations for 0 successes. 0 successes, all 20 failures. Here's that probability. And oh yeah, don't worry, we could get that right here. Remember, that was right here. The probability of 0 was 0.0617. And then now I'm going to do 1 minus that because I don't want 0 successes. I want everything other than 0 successes. So if I do 1 minus that, I'll get my answer a lot faster, 0.9383. All right, let's do another one here. What is the probability of at most 4? All right, what does at most 4 mean? That means 4 or less. That'd be 4 or 3 or 2 or 1 or 0. That's the probability of at most 4. I do not want 5. I do not want 6. I do not want 7. I do not want 8. So again, one thing I could do is just go to Desmos here, click on 0, 1, 2, 3, and 4, and add those probabilities together. At most 4 means 4 or less. So I'm going to add those probabilities together and I'll get my answer. But there's an even easier way. Check this out. On the left-hand side here, once you created that binomial distribution, click on cumulative probability. This allows you to look in between two values, outside of two values, to the left of a value, or to the right of a value. So I want to do 4 or less. So if I click on left, which is to the left or less, and then notice what it says. It says x less than or equal, and I'm going to type in a 4 there. And boom, there's the answer, 0.892. So it could do, using this little feature over here, it could do above, below, in between, or even outside. So at most 4 means 4 or less. So I'm choosing left. And notice it even highlighted those 4 things for me. The 0, the 1, the 2, the 3, and the 4. And it's going to add them all together for me. So that means I could get my answer very, very quickly with literally showing no work, 0.892. All right, let's do another one like that. What is the probability of at least 3? Okay, at least 3 means 3 or more. Anything greater than or equal to 3. So I'm going to go ahead and use this awesome feature here on the left. I'm going to hit right, and that means greater than or equal. And I'm going to type in a 3 there. So it literally says when I'm looking for x greater than or equal to 3, and we get 0.492. So just make sure that you do a couple things, right? Even though we're using the calculator to get our answer for us, we still have to be able to properly notate what it is we're looking for. We're trying to find the probability that the number of left-handed people is greater than or equal to 3, and our answer is 0.492, but we got to make sure we notate that answer. So don't just blindly give 0.492. I guess a multiple choice, you could do that, but we also have to understand what we're representing there with our answer. All right, let's do one more thing here. What is the mean and standard deviation, and interpret them in context. So what this means is we want to find the parameter. So if we were to look at 20 people and write down how many of them are left-handed, look at another 20 people, write down how many of them are left-handed, look at another 20 people, write down how many of them are left-handed, and do this repeatedly, the mean for the random variable h would be how many of those people are going to be left-handed in the long run. Okay, so pretty easy formulas here that we already showed you. These formulas only work if you are working with a binomial random distribution. So we're going to take 20 times 0.13 and we get 2.6. That means we expect 2.6 left-handed people in a group of 20. but that number could vary. It could be a little more, it could be a little bit less because, well, everything in the world varies. So now we're going to calculate the standard deviation by taking 20 times 0.13 times the failure rate, 0.87, and don't forget that giant square root, and we get 1.504. So if in a group of 20 people, I would expect an average of 2.6 left-handed people, but that number of left-handed people could vary by 1.504. So that's exactly how you would interpret it. The formulas are pretty easy, but make sure to interpret. Now, on the formula sheet for the AP statistics, will be given those formulas for you. They will give you these formulas right here for the parameters of a binomial random variable. And they will also give you this formula right here that shows you how to calculate the probabilities, even though I showed you how Desmos could do so much of it for you really, really easy. All right, I know it's a long video, but hopefully it was a really good description of the binomial distribution and how to calculate probabilities inside of it.